Let's find the volume of a sphere by using slicing. Um, so let's just take an example of a sphere of radius 5. If let me draw a picture of the sphere, it looks something like that, right? That's some sort of sphere. And we're going to slice it, right? So we're going to take a slice maybe up here would look something like that, right? The slices, if we slice it, we're slicing it horizontally. The slices are going to be circles, and we're going to need to find the area of each slice. And so how are we going to do that? Well, the first thing, the thing that I keep saying is super important here is to actually always draw coordinates. So you want to coordinatize your situation. So let's put a y-axis here. This is the slice at height y. What we want to do is we're going to want to find the radius of the slice at height at height y, right? We're going to want that radius. But the question is, where should we put, like, for example, where should we put y equals 0? Should we put it at the bottom of the sphere, or at the top of the sphere, or in the middle of the sphere? I think that because of the sort of the symmetry of the sphere, and also because if you think about it, there's like an equivalent slice down here at the bottom, in the bottom half. There are slices down there. It turns out that I think it makes sense. It's going to be sort of easiest if we make y equals 0 right in the center. Right, so that's going to be y equals 0 right in the center of the sphere. So then down here would actually be -5. Remember this, the radius of the sphere is 5. So the total height is 10, and so it's 5 up and 5 down. So down there would be -5. At the top would be y equals +5. And we would like to find the radius as a function of the height, right? So like, again, we're going to find a of y. A of y is the area of the slice at height y. And it's pi r squared, where r is also kind of a function of y, right? Where r is the radius of the slice at height y. Okay, so for example, some examples again we've seen, like if we want a of 5, right? Like what's a of 5? A of 5 is going to be 0 because there's no slice at the very top, right? The slices get smaller and smaller at the top, and as you get closer and closer to the top, they kind of vanish. Similarly, a of -5 will be 0. But the area of the slice at height 0 is right in the equator, right? It's the sort of equatorial slice. And that has radius 5 because that's the radius there. So that's pi times 5 squared. So that's 25 pi. So we need some function of y that when we plug in 0, we get 25 pi, but when we plug in plus or minus 5, we get 0. And so how are we going to do that? So let's, again, look at the side view of the sphere. So I'm going to kind of want to like shine a light on the sphere from the side. And the shadow would just be a circle, right? So let's think about this circle. Again, let me put my axes on the picture because that's going to be useful. So my axis, I guess, is only singular axis. And we have the center of the sphere right there. We know that's a radius of 5. This is y equals 0. The radius that we really want, we kind of want to go up to height y, right? So if I go up to a specific y, and think about the height there, well, here that's your radius, right? That's your radius r. If you look back at the picture on the left, the slice in the northern hemisphere, that's sort of, again, if we squash the whole picture flat 2D from the side, that's what we're looking at, is the radius r right there. And when we had a cone, the key turned out to be using similar triangles. When we have a sphere, again, we want to find r as a function of, we want to find the radius r as a function of y. I'm going to draw in a couple more things to this picture. So first there's this, which we know is y, right? We know that height is y because it's from 0 up to height y. And here's the sort of slick thing to do, is if you actually draw a radius from the center out to the edge of r, so that's length 5, right? And if I pick, let me move this r, move it up here above. So that's r right there. This is a right angle. Maybe I'll just make this whole triangle red. So we've got this triangle right here. And we know it's a right triangle. We know all 3 sides of it. So actually, let me draw that triangle down here. It's supposed to be a right triangle. That side's r, that side's y, that side's 5. And our favorite theorem, the Pythagorean theorem, says that y squared plus r squared equals 5 squared, right? And in fact, so we want r as a function of y. So then that means, let's see, if we want to solve for r, we get r squared is 25 minus y squared. And then that means r is in fact the square root of 25 minus y squared. And so there you go. We found a formula for the radius as a function of the height y, the radius of the slice, I should say. The radius of the whole sphere is 5, but the radius of each of the circular slices, the horizontal slices, change. And that means actually then the area, if we want to think about what the area formula says, we said it's pi r squared. So you actually don't even need the square root. You get pi times 25 minus y squared. It's nice. That's what r squared is, right? And again, you can check a of 0. If you go back to the top and you check these against the formula, let me put the formula that we just found up here, pi times 25 minus y squared. Well, what if we plug in 5 or negative 5 for y, right? That becomes 25 minus 25. So that leads to both of these, check, check. And if we plug in 0 for y, well, we get 25 minus 0 squared. So we actually get 25 pi. So that's also checked. So that formula does work. You can sort of check it against. It's a good idea to check these formulas that you find against the situation and see if it's makes sense as a formula. Okay, so then the rest is, like we've said, to find the volume, we just want to integrate this slice, the area of the slice function. And where are we integrating it from? Well, again, the sphere starts at the bottom of the sphere is at height -5, and the top of the sphere is at height 5. So there are slices all the way from y equals -5 to y equals 5. And so that ends up becoming our integral. And so we integrate from -5 to 5, 25 minus y squared dy. And hey, that's pretty nice, right? So it's pi times, we do 25 becomes 25y, y squared becomes 1/3 y cubed. We evaluate from 0 to 5. We get pi times 25 times 5 minus 1/3 of 5 cubed. Minus, when we plug in 0, everything becomes 0, right? And so you do some of this, I don't know, you could be a little bit slick here by thinking of this also as a 5 cubed. So I could actually pull a 5 cubed out. So this is really pi times 5 cubed times 1 minus 1/3. Oh, I messed up. Oh my God, I messed up, guys. I did from 0 to 5. Why did I do that? It was from -5 to 5. Oh my God. It turns out you get half the volume of the sphere this way. I really should have put in the -5 though. Oh, so bad job by me. Let's erase all this. Sorry. Okay, so this should be -5. That's fine. I mess up. Oops. -5. Okay. So now that's pi. Now you do have to put in everything. So you get 25 times 5 minus 1/3, 5 cubed, minus 25 times -5 minus 1/3 of -5 cubed. And you get some interesting things here happen. Sadly, this doesn't cancel. This minus makes a plus. And now we've got a bunch of minuses, so that's a plus there. These minuses, there's 4 minuses because there's 3 minuses right here, and then there's another minus right here, so that's a plus. But with this minus, it really becomes a minus. So, okay, so it's kind of being kind of silly here, but we get pi, we get times 20, we get times 5 cubed. I'm gonna write that 25 times 5 is 5 cubed, minus 1/3 5 cubed. We get plus another 5 cubed, and then we get minus another 1/3 5 cubed. And I'm gonna pull the 5 cubed out. So we get pi times 5 cubed times 1 minus 1/3 plus 1 minus 1/3. So 2 minus 2/3, that's 4/3. So we get, yeah, this simplifies to 4/3. And so we actually get as our final answer 4/3 times pi times 5 cubed. And if you've ever seen this formula, it turns out that this is the general formula. The general formula for the volume of a sphere of radius r is actually 4/3 pi r cubed. And let me use capital R or something like that because it's a different, you know, it's this. I don't want to use the same little r that I used there. So that's actually turns out to be the formula for the volume of a cube, volume of a sphere. And was I saying volume of a cube? Let's hope not. Do this video too late at night. I think my brain's not working as well as it should be. Okay. So yeah, so that's this is an example of the general volume formula for a cube. And all right, that is it. Have a good night.